Now here's an example of what's called an IR transmission spectrum for carbon dioxide. This is a spectrum which comes from a piece of equipment called an infrared spectrometer. And in this type of equipment, what you do is you have an infrared source, which is like a glowing filament, a hot filament, almost like, you know, in a regular incandescent light bulb, you have a glowing filament. So you have a glowing filament, so I'll make it look like a glowing filament inside this machine, and it's going to give off infrared radiation because it's hot, okay, and you're going to kind of focus the infrared radiation towards a sample, whatever you're interested in exposing to the infrared radiation. In this case, carbon dioxide is going to be in this sample. And then you're going to allow the infrared radiation to pass through the sample, and at all different wavelengths. You are allowing, you know, one wavelength at a time to pass through this particular sample, okay? And only certain wavelengths are going to come out on the other side. And the wavelengths that are absorbed by the carbon dioxide are not going to come out on the other side. You're going to detect this with some kind of a detector on the other end. Okay? And so this is called an IR spectrum. This would be what you see on your detector on the other end. And what it is you have percent transmittance on this side, and you have wave number down here. Now wave number is kind of strange. It is another way of representing the wavelength. Only normally for the wavelength for infrared radiation, you're going to be in the micrometer range, and but traditionally infrared spectroscopists, the people who do this kind of work, chose to convert the micrometer wavelength unit into wave number units, which are inverse centimeters. And so the conversion, one wave number equals 1 over a micrometer times 10,000. And the reason why they did this was because the wave number matches or correlates directly with energy, since it's the inverse of the wavelength. And remember, there's an inverse relationship between wavelength and energy. So in other words, if the higher wave number is higher energy, lower wave number is lower energy. So it's just a way that they have traditionally expressed wavelengths in terms of wave numbers, so that the bigger wave number corresponds to higher energy transitions. All right, so don't let that confuse you. It's still a measure of the wavelength, or just a way to separate the different types of infrared radiation. To make a long story short, what happens is you're exposing this sample, carbon dioxide, to infrared radiation of varying wave number or wavelength, and the transmittance is how much is getting through. And 95%, most of the infrared light is getting through. Maybe a little bit is being absorbed by, some other gases that are in the sample or the container or whatever. And then all of a sudden you have this decrease to zero transmittance. That means at this particular wave number, no IR is getting through. That means it's being absorbed by your sample. Okay? And so we have two major areas where there's an absorption of infrared radiation. This one is at about 2,400 or so nanometer or wave numbers, which is the same as 4.26 microns. And this one here is at about 15 microns, which is looks like about 700 wave numbers. Okay, that's about 15 microns. Okay, shorter wavelength, higher energy; longer wavelength, lower energy; higher wave number, higher energy. So this is a higher energy transition, and this is a lower. And this is the one that corresponds to the stretching, and this is the one that corresponds to the bending. And that makes sense because we said that the stretching takes more energy than the bending. Think of a slinky. It takes more energy to stretch it than to bend it. It just kind of flops back and forth. Okay? So indeed, this is evidence that carbon dioxide absorbs infrared radiation. It absorbs it because of the what they call vibrational modes of the carbon dioxide, the ability of carbon dioxide to stretch asymmetrically and to bend. And so it's in the range of the infrared infrared region, and so that's where it's absorbed. All right?